Um, Good morning, everyone. So I will explain the next part of what Kritika said. I mean, that was a numerical study, and I will explain what are the analytical things and how far can we do analytically in this part. I mean, what in the connection between return probability and autocorrelation. So this is the thing I am doing in the last 6 months in collaboration with Sridhari and Kritika. So, um, so in the last 15 minutes, you got the idea that we want to connect some spatial temporal correlation in real space and Fock space dynamical quantity. So why we are interested in this question? Because there is lots of work in finding out real space dynamical quantities in this many body localization on field or in this, I mean, I want to mean in general disordered spin chain field. And there are also lots of work has been done on this Fock space dynamical quantities. So we want to find out, I mean, is there some connection? Is there some one-to-one connection in between dynamical quantities in these two spaces? So what can be the simplest question in this connection? So as Kritika was saying that since autocorrelation and return probability both says about the how much memory it preserves after a certain time. So we want to understand. We believe that that is the simplest question we can answer to find out the connection between real space and Fock space. So this is these are the things. I mean, she said that C of t is the infinite temperature autocorrelation return probability. If we start with the product state, what is the probability after some time after unitary evolution to again come into the same state? And this is the Hamming distance. Hamming distance basically this is the definition of distance in Fock space. So we will connect these two by introducing Fock space correlator. So this is G of R, T, and where R is the Hamming distance. Okay, not real space distance. Okay, and we define this Fock space correlator by introducing that if we start with the initial state, if we do some unitary evolution, and what is the probability to go some kth product state. But the distance between R, I, and K is R, and this is the sum over NR, where NR is the number of states at a distance R from the initial state. We also took that sum over G of T is equal to 1 because since it is a unitary evolution, and if you see the expression of return probability and the G of T from this two expression, you can say that return probability is just equal to G of 0, T. And the autocorrelation figure, the autocorrelation thing, this can also be written in terms of G of T and the Fox, this Hamming distance by this. I mean, C of T is equal to 1 minus 2 into R average over L. So the two important things from this slide is that the return probability and the autocorrelation can be related by this Fock space correlator, and they are related in this way. I mean, G of 0 is return probability, and G of, I mean, average of Hamming distance is C of T. So that's why we want to know what is the spatial temporal structure of this Fock space correlated G of T. So I mean, we plotted this this thing 1 over L log of G of T over NR, and in the x-axis we plot R over L. So we want you can see that so different color correspond to different time. The below one is for t equal to 100, and the above the red one is for t equal to 50. So since all the curves collapses for different system size, so we can say that this can be the behavior of the thermodynamic in the thermodynamic limit, since I mean it's a finite system numeric. So since all the curves collapses here, so we can say that this is a infinite temperature. It can be infinite temperature dynamics, and so from here we can say that this y-axis thing, this 1 over L log of G of T over NR is something minus f of x comma t, since what we define the x is some R over L. Okay. And I mean it's indeed a function of R over L, not just some other function of R over L. We really don't know why it's like that, but I mean it is what we got. I mean after numerical doing it. So these are the expression I was saying. We split this capital F of x comma t in two terms, small f of x comma t and minus 1 over L log of RT, because see, I mean at long time the right hand side should be independent of R, because this is a Fock space correlator. I mean it will not have some space dependence at a long time. So That's why we wrote the r equal to 0 term separately. I mean, this 1 over L log of RT is r equal to 0 term. And okay, and this NR is basically, I mean, what I was saying that NR is number of Fock space states at a distance r from the initial state. And this is actually LCR in that Hilbert space graph, what Kritika was saying. And LCR can be, I mean, approximated as like a Gaussian with mean around L by 2 and mean around L by 2 and standard deviation around L by 4. So, and sigma square around L by 4. So, and I also said that, I mean, since non-preserved sum over r g of RT should be equal to 1, this is just the integral form of that equation. So, this I wrote this equation, I mean, here, I mean, I just wrote g of RT from here and I got this equation, okay. And from this, you can see this thing, I mean, in the exponent, I mean, this f of x comma t plus 2 into x minus half squared, this is the function, I mean, we'll do this integration using saddle point approximation, and this integration has a saddle point around x equal to x star. I mean, at x equal to x star, where x star satisfies this equation. And if you can remember that in the second slide, I showed that C of t is just 1 minus 2 r over L by L. Since it was r over L by L, that we can, I mean, doing this saddle point integration and all this business, I mean, we can say 1 minus, this is a 1 minus 2 into x star. For x star, which x star we can find from this thing. Okay. And doing this, all this calculation, we will get C of t is just half into del x f of x comma t at x equal to x star, and log of RT over L minus log of R infinity over L is this thing. So now, I mean, our initial goal was to connect return probability and autocorrelation. So now, I mean, after simplifying all of these things, we can see that these two are connected by this f of x comma t thing. I mean, it is something that decides how these two things are connected. And also, I mean, the second term is simply just c square by 2. But we don't know, I mean, how C of t is hidden in this term. So, I mean, that's what I was saying. I mean, these two dynamical quantities is connected by the function f of x comma t. So we plotted here the derivative, I mean, at x equal to at the saddle point, and also the function at the saddle point. Now we see that this is sort of some linear behavior in the log scale. So from here, I mean, we conclude that this f of x comma t is related in this way. It's, I mean, f of x comma t at its saddle point is related to the derivative in this fashion. Okay, so finally we got, I mean, the second term was, as I was saying, just c square by 2, and just first term was just f of x comma t at the saddle point, which we can write as a into c of t to the power alpha. So, I mean, using this relation, we can say about, I mean, what do we expect for different models? So, for the transverse field Ising model, we know that the autocorrelation functions decays quickly because there is no conservation law, so it decays like a stretched exponential. And doing all using this relation, we can say that the return probability also decays like a stretched exponential. Just the prefactor in the stretched exponential will change. I mean, it was lambda in the autocorrelation, it will be just lambda alpha. And for the executive model, since there is conservation law and all, it, I mean, in general, it decays like a power law. I mean, if it is subdiffusive and all. And so C of t is proportional to the minus alpha. If we do all these things, I mean, we got the return probability, I mean, the thermodynamic quantity, that is RT to the power 1 by L, that that approaches to R infinity to the power 1 by L like a power law, but this power is, I mean, this is alpha gamma in much more than what it was before. Okay, and okay, so this is the final relation and what we are trying to get, and what are the things we can understand from this thing is initially in many body localization field there are two types of picture. I mean, people are looking at real space dynamical quantities and Fock space dynamical quantities like autocorrelation and return probability. By this one-to-one connection, we can relate these two pictures. This also gives a better understanding because it also gives how this higher dimensional Hilbert space information is embedded into the real space dynamical quantities. And also one more thing, I mean, since it's very hard to do analytical calculation in this many body problem because there is disorder, interaction and all. So, I mean, simplifying a many body problem to a single particle, single fictitious particle problem on a high dimensional correlator, high dimensional graph, it will help us to do analytical advancement as much as possible. Thank you.
So, audience may ask questions if they have.
Yeah, can you hear me? Yeah. Could you remind me which was the value of gamma for which there was a phase transition sort of thing, like between delocalized and localized? I think it was 0.3 or something.
0.3, yes.
Yeah. So can I?
Okay, continue.
Yeah. First, this alpha contains the information of gamma, right? Of the value of gamma. From whatever you're deducing from this relation between del x f.
Yes,
and
that
f.
we need to say. I mean, this A also may contain this disorder information. So, and this is far in the ergodic phase. I mean, since it's for gamma equal to 0.5, 0.6, and it's above.
So I was trying to say, like both A and alpha contain indirectly or directly information of gamma.
Yes.
My point is that can you stretch this result to 0.3, like gamma equal 0.3? Can you somehow, because in that phase, I mean at the critical point, so to say, can you extrapolate this formula?
That we have to see, but what I think is near the transition, the physics behaves differently, I guess. I mean, so I mean, all the analytical calculation we have done is only for the ergodic region. Near the transition, we have to see. I mean, I am not sure whether we can extrapolate this at gamma equal to 0.3 or not.
Okay, maybe I can ask this then. Like, is it true that far away from the critical, like for larger values of gamma, you have better? I mean, that law holds better, the formula that you have derived?
Yes, it holds better. I mean,
okay, yeah.
So earlier in some plot, you talked about collapsing of curves for different system size. Yeah, from here you are concluding that even for different system size, they collapse but so you can consider the results to be valid for thermodynamic limit. But I mean, we are not seeing exactly collapsing, like at the end, they are not collapsing. What kind of collapse are you talking
about? Yes, I mean, see, I plotted for, 100, 300, and 500 T. And for, it collapses. I mean, maybe you can say it collapses poorly, but I mean, if we go for small time limit, it will collapse better. And see, I mean, if we increase time, and system will get to know about the finite stage effect. I mean, with increasing time, it will collapse bad.
Oh, you're saying that it collapsing to those red and blue curves eventually?
No, I am saying this different colors correspond to different time.
Different time. Okay.
Yes. Okay. Sorry for the confusion. I mean, different color correspond to different time, and different marker correspond to different system size.
I see.
So, I mean, these are for T equal to 100, 300, and 500.
Okay. Thank you.
More questions?
One thing I missed. Can you go to that formula? You have alpha, derivative to the power alpha. This next slide. This alpha. You showed that this alpha is same as the power law decay of CT e power alpha.
Oh, sorry for the confusion. Sorry. I should write here. Sorry. I should write here some other thing, beta or something like that. Sorry.
So the question is, how do you determine this alpha numerically?
Sorry, I mean, I wrote here gamma. This should also be gamma. Sorry. Yes.
And you determine alpha, this alpha.
Yes.
Numerically, is there any argument to compute it or?
Sorry, I mean, you are asking about this alpha, right?
Yeah.
This alpha we can find out numerically from this plot. I mean, we didn't do it yet, but we can do it from there, right? I mean, finding the slope and all that.
And last question, this formula that you are trying to establish, how will it change if we introduce interactions, more, let's say, power law type interactions among the spins in the real space? Still, you have thermodynamic limit, suppose.
Okay.
Have any thoughts?
You were saying about power law type interaction. I'm not sure. I mean, I have to say. Thank you.
Thank you, Bikram.